In this video, we shall look at the concept of inductance. Let's assume you have two coils, one here and one there. Let's call the red coil coil 1 and the green one coil 2. There are N1 turns in coil 1 and N2 turns in coil 2. Coil 1 carries current I in the direction shown. Coil 2 does not have any current. Let's look at coil 1. Since it has electric current, it would produce magnetic field in the direction shown. Like that. So this is the magnetic field due to coil 1. Obviously, this field is also passing through coil number 2. Now let's assume the current in coil 1 changes. So there is di dt. It could be increasing with respect to time or decreasing with respect to time. It doesn't matter at this point. When that happens, the magnetic field it creates will also change with respect to time. Since the magnetic field is also passing through coil number 2 also have magnetic flux through it. And since this magnetic flux is created by that magnetic field, and this magnetic field is changing with respect to time, that implies the magnetic flux through coil 2 also changes with respect to time. What that means is there must be an induced EMF in coil number 2, and that induced EMF is given by the following expression. This is just Faraday's law. One thing to note is this magnetic flux through coil number 2 is directly related to the current in coil number 1. So we can simply write magnetic flux in coil number 2 is proportional to current in coil number 1. There are N2 number of turns in coil number 2, so N2 times the magnetic flux in coil number 2 is proportional to the current in coil number 1. Let's take the proportionality constant to be m. So we can write the proportionality in terms of equation in a following manner, like that. So from this equation, we can immediately see that N2, rate of change of magnetic flux in coil 2, equals m di dt, or rate of change in current in coil 1. So substituting this result in this expression for EMF induced in coil 2, we can write down an expression for EMF in coil 2 in terms of a rate of change of current in coil 1, namely minus m di dt. The constant m is called the mutual inductance of the system. It can be quantified in the unit of Henry, or abbreviation capital H. That is the SI unit to calculate inductance. Of course, the inductance can also be calculated directly from that equation as being N2 flux in coil 2 over current in coil 1. Now let's assume we reverse the roles of the coil. Now coil 2 carries current in that direction, let's say. Let's call that current I. What happens in this case, it creates magnetic field, and that magnetic field will pass through coil number 1, but it's created by current in coil number 2. In this case, we talk about EMF induced in coil number 1 as given by the following expression. Of course, we can take the current as not I, but as, let's say, I2. So in general, it is different from the original I that we talked about earlier when the current belonged to coil number 1. The point is to note that constant of proportionality. In both cases, it turns out we have the same constant of proportionality, namely the inductance of the system is identical. For that reason, it is called mutual inductance. Now, let's assume you have just a single coil, like that, and it carries current in that direction, let's say. So that means there must be magnetic field through the coil like that. Let's call it B. Let's assume the current is I, the number of turns in that coil is N. If I changes, that means the magnetic field would also change. That implies the magnetic flux through the coil must also change. Now that means there must be an induced EMF in this coil itself. So the EMF is given by minus N d flux dt. As for the case with two coils, the magnetic flux through this coil is proportional to the electric current through it. And like before, we can turn this proportionality into equation in a following manner. The number of turns times the magnetic flux equals a proportionality constant L times the electric current. Now this proportionality constant is known as self-inductance of that coil. Self because there is only one coil now. And using that equation, we can also write the induced EMF in a following manner, minus L di dt. If there is an induced EMF in that circuit, there must also be an induced current in it. What is the direction of that induced current? So the original current is in that direction as a whole. Let's look at two cases. Case 1, when that original current increases with respect to time. So that means this is positive. That would make the EMF negative. And the direction of the induced current is the same as the direction of the induced EMF. So it opposes the increasing current, so which means the direction of that induced current will be going like that. With the net result, the direction of the induced EMF and induced current opposing the original increasing current, namely in this direction. Or if you want to label on the diagram, it goes like that, in that direction. Now let's look at case number 2, when the current is decreasing with respect to time. That means, according to this equation, the EMF is positive, or we can say that the induced EMF E opposes this decrease, and along with it, the induced current is also positive. So the direction of that induced current will be the same as the direction of the original current to make up for that decrease. So namely, it's going to go like that. Now let's look at a problem. Two coils have mutual inductance of 0.04 Henry. The current I1 in the first coil increases at a uniform rate of 0.06 ampere per second. What is the induced EMF in the second coil? So you have the first coil and then you have the second coil. The mutual inductance of the system is 0.04 Henry. The current in the first coil, that is di dt, increases with respect to time 0.06 ampere per second. So the magnitude of this induced EMF can be calculated using this equation. So mutual inductance is 0.04 Henry, di dt is 0.06 ampere per second, and that's going to give you 2.4 times 10 to the power minus 3 volt for the induced EMF. Problem 2. A current in the coil with inductance of 40 microhenry as shown increases uniformly from 0 to 8 ampere in 0.5 seconds. Find the magnitude and the direction of the self-induced EMF. So the magnitude of the EMF is just L di dt. This L is the self-inductance. So L is 40 microhenry, so 40 times 10 to the power minus 6. Di dt can be calculated. It goes from 0 to 8, so 8 minus 0 in 0.5 seconds. So that is the rate of change of current. And when you calculate that, you get 6.4 times 10 to the power minus 4 volts. Now let's work out the direction. This is magnitude. So the expression for EMF, taking into account the direction, is given by this equation. If this is increasing, namely this is positive, this negative would imply the EMF to be negative. So this induced EMF must oppose the increasing current. So that direction then must be that way. That is also the direction for the induced current. And that solves the problem. As always, thank you for watching.